Electricity is the set of physical phenomena associated with the presence and motion of matter, possessing an electric charge. Electricity is related to magnetism, both being part of the phenomenon of electromagnetism, as described by Maxwell's equations. Common phenomena are related to electricity, including lightning, static electricity, electric heating, electric discharges, and many others. The presence of either a positive or negative electric charge produces an electric field. The motion of electric charge carriers is an electric current and produces a magnetic field. In most applications, Coulomb's law determines the force acting on an electrically charged particle. Electric potential is the work done to move an electric charge from one position to another within an electric field, typically measured in volts. Electricity plays a central role in many modern technologies, serving in electric power, where electric current is used to energize equipment, and in electronics dealing with electrical circuits involving active components such as vacuum tubes, transistors, diodes, and integrated circuits, and associated passive interconnection technologies. The study of electrical phenomena dates back to antiquity, with theoretical understanding progressing slowly until the 17th and 18th centuries. The development of the theory of electromagnetism in the 19th century marked significant progress, leading to electricity's industrial and residential application by electrical engineers by the century's end. This rapid expansion in electrical technology at the time was the driving force behind the Second Industrial Revolution, with electricity's versatility driving transformations in both industry and society. Electricity is integral to applications spanning transport, heating, cooling, lighting, communications, and computation, making it the foundation of modern industrial society. Long before any knowledge of electricity existed, people were aware of shocks from electric fish. Ancient Egyptian texts dating from 2750 BCE described them as the protectors of all other fish. Electric fish were again reported millennia later by ancient Greek, Roman, and Arab naturalists and physicians. Several ancient writers, such as Pliny the Elder and Scribonius Largus, attested to the numbing effect of electric shocks delivered by electric catfish and electric rays, and knew that such shocks could travel along conducting objects. Patients with ailments such as gout or headache were directed to touch electric fish in the hope that the powerful jolt might cure them. Ancient cultures around the Mediterranean knew that certain objects, such as rods of amber, could be rubbed with cat's fur to attract light objects like feathers. Thales of Miletus made a series of observations on static electricity around 600 BCE, from which he believed that friction rendered amber magnetic, in contrast to minerals such as magnetite, which needed no rubbing. Thales was incorrect in believing the attraction was due to a magnetic effect, but later science would prove a link between magnetism and electricity. Electricity would remain little more than an intellectual curiosity for millennia, until 1600, when the English scientist William Gilbert wrote De Magnete, in which he made a careful study of electricity and magnetism, distinguishing the lodestone effect from static electricity produced by rubbing amber. He coined the Neo-Latin word electricus, of amber or like amber, from letter 1 F24 lambda epsilon kappa tau rho omicron nu, electron, the Greek word for amber, to refer to the property of attracting small objects after being rubbed. This association gave rise to the English words electric and electricity, which made their first appearance in print in Thomas Brown's Pseudodoxia Epidemica of 1646. Isaac Newton made early investigations into electricity, with an idea of his written down in his book Optics, arguably the beginning of the field theory of the electric force. Further work was conducted in the 17th and early 18th centuries by Otto von Guericke, Robert Boyle, Stephen Gray, and C. F. Dufay. Later in the 18th century, Benjamin Franklin conducted extensive research in electricity, selling his possessions to fund his work. In June 1752, he is reputed to have attached a metal key to the bottom of a dampened kite string and flown the kite in a storm-threatened sky. A succession of sparks jumping from the key to the back of his hand showed that lightning was indeed electrical in nature. He also explained the apparently paradoxical behavior of the Leyden jar as a device for storing large amounts of electrical charge in terms of electricity consisting of both positive and negative charges. In 1775, Hugh Williamson reported a series of experiments to the Royal Society on the shocks delivered by the electric eel. That same year, the surgeon and anatomist John Hunter described the structure of the fish's electric organs. In 1791, Luigi Galvani published his discovery of bioelectromagnetics, demonstrating that electricity was the medium by which neurons passed signals to the muscles. Alessandro Volta's battery, or voltaic pile, of 1800, made from alternating layers of zinc and copper, provided scientists with a more reliable source of electrical energy than the electrostatic machines previously used. The recognition of electromagnetism, the unity of electric and magnetic phenomena, is due to Hans Christian Ørsted and André-Marie Ampère in 1819-1820. Michael Faraday invented the electric motor in 1821, and Georg Ohm mathematically analyzed the electrical circuit in 1827. Electricity and magnetism and light were definitively linked by James Clerk Maxwell, in particular in his On Physical Lines of Force in 1861 and 1862. 148. While the early 19th century had seen rapid progress in electrical science, the late 19th century would see the greatest progress in electrical engineering, through such people as Alexander Graham Bell, Otto Blathy, Thomas Edison, Galileo Ferraris, Oliver Heaviside, Ennios Jedlik, William Thomson, 1st Baron Kelvin, Charles Algernon Parsons, Werner von Siemens, Joseph Swan, Reginald Fessenden, Nikola Tesla and George Westinghouse. Electricity turned from a scientific curiosity into an essential tool for modern life. In 1887, Heinrich Hertz, 843-44, discovered that electrodes illuminated with ultraviolet light create electric sparks more easily. In 1905, Albert Einstein published a paper that explained experimental data from the photoelectric effect as being the result of light energy being carried in discrete quantized packets, energizing electrons. This discovery led to the quantum revolution. Einstein was awarded the Nobel Prize in Physics in 1921 for his discovery of the law of the photoelectric effect. The photoelectric effect is also employed in photocells, such as can be found in solar panels. The first solid-state device was the cat's whisker detector, first used in the 1900s in radio receivers. A whisker-like wire is placed lightly in contact with a solid crystal, such as a germanium crystal, to detect a radio signal by the contact junction effect. In a solid-state component, the current is confined to solid elements and compounds engineered specifically to switch and amplify it. Current flow can be understood in two forms, as negatively charged electrons, and as positively charged electron deficiencies called holes. These charges and holes are understood in terms of quantum physics. The building material is most often a crystalline semiconductor. Solid-state electronics came into its own with the emergence of transistor technology. The first working transistor, a germanium-based point-contact transistor, was invented by John Bardeen and Walter Hauser-Brattain at Bell Labs in 1947, followed by the bipolar junction transistor in 1948. By modern convention, the charge carried by electrons is defined as negative, and that by protons is positive. Before these particles were discovered, Benjamin Franklin had defined a positive charge as being the charge acquired by a glass rod when it is rubbed with a silk cloth. A proton, by definition, carries a charge of exactly 1,602,176,634 times 10⁻19 coulombs. This value is also defined as the elementary charge. No object can have a charge smaller than the elementary charge, and any amount of charge an object may carry is a multiple of the elementary charge. An electron has an equal negative charge, that is -1. 602,176,634 times 10⁻19 coulombs. Charge is possessed not just by matter, but also by antimatter, each antiparticle bearing an equal and opposite charge to its corresponding particle. The presence of charge gives rise to an electrostatic force. Charges exert a force on each other, an effect that was known, though not understood, in antiquity. A lightweight ball suspended by a fine thread can be charged by touching it with a glass rod that has itself been charged by rubbing with a cloth. If a similar ball is charged by the same glass rod, it is found to repel the first. The charge acts to force the two balls apart. Two balls that are charged with a rubbed amber rod also repel each other. However, if one ball is charged by the glass rod, and the other by an amber rod, the two balls are found to attract each other. These phenomena were investigated in the late 18th century by Charles Augustin de Coulomb, who deduced that charge manifests itself in two opposing forms. This discovery led to the well-known axiom, like-charged objects repel and opposite-charged objects attract. The force acts on the charged particles themselves, hence charge has a tendency to spread itself as evenly as possible over a conducting surface. The magnitude of the electromagnetic force, whether attractive or repulsive, is given by Coulomb's law, which relates the force to the product of the charges and has an inverse square relation to the distance between them. The electromagnetic force is very strong, second only in strength to the strong interaction, 38, but unlike that force it operates over all distances. In comparison with the much weaker gravitational force, the electromagnetic force pushing two electrons apart is 1042 times that of the gravitational attraction pulling them together. Charge originates from certain types of subatomic particles, the most familiar carriers of which are the electron and proton. Electric charge gives rise to and interacts with the electromagnetic force, one of the four fundamental forces of nature. Experiment has shown charge to be a conserved quantity, that is, the net charge within an electrically isolated system will always remain constant regardless of any changes taking place within that system. Within the system, charge may be transferred between bodies, either by direct contact or by passing along a conducting material, such as a wire. The informal term static electricity refers to the net presence or imbalance of charge on a body, usually caused when dissimilar materials are rubbed together, transferring charge from one to the other. Charge can be measured by a number of means, an early instrument being the gold leaf electroscope, which, although still in use for classroom demonstrations, has been superseded by the electronic electrometer. The movement of electric charge is known as an electric current, the intensity of which is usually measured in amperes. Current can consist of any moving charged particles. Most commonly these are electrons, but any charge in motion constitutes a current. Electric current can flow through some things, electrical conductors, but will not flow through an electrical insulator. By historical convention, a positive current is defined as having the same direction of flow as any positive charge it contains, or to flow from the most positive part of a circuit to the most negative part. Current defined in this manner is called conventional current, the motion of negatively charged electrons around an electric circuit. One of the most familiar forms of current is thus deemed positive in the opposite direction to that of the electrons. However, depending on the conditions, an electric current can consist of a flow of charged particles in either direction, or even in both directions at once. The positive to negative convention is widely used to simplify this situation. The process by which electric current passes through a material is termed electrical conduction, and its nature varies with that of the charged particles and the material through which they are traveling. Examples of electric currents include metallic conduction, where electrons flow through a conductor such as metal, and electrolysis, where ions-charged atoms flow through liquids, or through plasmas such as electrical sparks, while the particles themselves can move quite slowly, sometimes with an average drift velocity only fractions of a millimeter per second. The electric field that drives them itself propagates at close to the speed of light, enabling electrical signals to pass rapidly along wires. Current causes several observable effects, which historically were the means of recognizing its presence. That water could be decomposed by the current from a voltaic pile was discovered by Nicholson and Carlisle in 1800, a process now known as electrolysis. Their work was greatly expanded upon by Michael Faraday in 1833. Current through a resistance causes localized heating, an effect James Prescott Joule studied mathematically in 1840. One of the most important discoveries relating to current was made accidentally by Hans Christian Ørsted in 1820, when, while preparing a lecture, he witnessed the current in a wire disturbing the needle of a magnetic compass. He had discovered electromagnetism, a fundamental interaction between electricity and magnetics. The level of electromagnetic emissions generated by electric arcing is high enough to produce electromagnetic interference, which can be detrimental to the workings of adjacent equipment. In engineering or household applications, current is often described as being either direct current (DC) or alternating current (AC). These terms refer to how the current varies in time. Direct current, as produced by example from a battery, and required by most electronic devices, is a unidirectional flow from the positive part of a circuit to the negative. If, as is most common, this flow is carried by electrons, they will be traveling in the opposite direction. Alternating current is any current that reverses direction repeatedly. Almost always this takes the form of a sine wave. Alternating current thus pulses back and forth within a conductor, without the charge moving any net distance over time. The time-averaged value of an alternating current is 0, but it delivers energy in first one direction, and then the reverse. Alternating current is affected by electrical properties that are not observed under steady-state direct current, such as inductance and capacitance. These properties, however, can become important when circuitry is subjected to transients, such as when first energized. Electric field. Main article: Electric field. See also Electrostatics. The concept of the electric field was introduced by Michael Faraday. An electric field is created by a charged body in the space that surrounds it, and results in a force exerted on any other charges placed within the field. The electric field acts between two charges in a similar manner to the way that the gravitational field acts between two masses, and like it extends towards infinity and shows an inverse square relationship with distance. However, there is an important difference. Gravity always acts in attraction, drawing two masses together, while the electric field can result in either attraction or repulsion. Since large bodies such as planets generally carry no net charge, the electric field at a distance is usually 0. Thus gravity is the dominant force at distance in the universe, despite being much weaker.